So this is the stepping stones video for the modern physics class, and this is I guess it's stepping stones video number 2. I'm going to try to index them this way. Yeah. Okay. So what you're doing right now or currently is you're working on issues that are brought up at the end of chapter 5. And the issues that are brought up are what are called potential steps and barriers. So, these just refer to particular values or particular functions, u of x. And a step is going to, well, you probably already know this, but a step looks like this. So the potential on the right-hand side, and this just is meant to continue to infinity, the potential on the right-hand side has a higher value than the potential on the left-hand side. And you can consider the case where the particle that's going to interact with this potential, the particle's energy can be above the top of the upper step, or it can actually be just above the lower part of the step, but underneath the upper part of the step. And those two cases are treated in your book. A barrier is different from a step because a step really only has two regions, say a region 1 and a region 2, that are qualitatively different in terms of writing down Schrodinger's equation. A barrier actually has 3 regions. It's two regions that are similar in potential. They have the same potential value, but they are separated by a region where the potential is higher. So this is going to be a barrier, and you can consider particles with energy below the top edge of the barrier, but also particles with energy above the top of the barrier. So pretty interesting. In this case, though, there are 3 regions. Okay. So let's see. Yeah, quite honestly, it starts off pretty straightforward. It starts with the step potential here, but it quickly, so it's a straightforward start, conventional. You take Schrodinger's equation, you stick in this particular potential, and that effort points you at some wave functions, where psi is, piecewise defined. It's psi 1 in region 1 and psi 2 in region 2. And these are simply the wave function as a function of x. So this is as a function of x. There's a whole bunch of unknown coefficients. In your book, these are a, b, c, d. And the wave functions themselves are written in terms of sine and cosine. And when your book is presenting this answer to you, it all is going to make sense. It's the same stuff as before for different potential situations. But it points out the fact that the sine and the cosine functions that are used as the building blocks of building up these wave functions, the sine and the cosine functions, these are real. Everything about our solution is real as far as the sine and the cosine goes, but the coefficients a, b, c, and d are the only place where any complexness shows up, any complex numbers. And so what the book does is it asks you to make a change. And instead of, for example, just using sines and cosines and then, these coefficients a, b, c, d, the suggestion is to rewrite the sines and the cosines in terms or using Euler's formula. So this is the cosine of theta plus or minus I times the sine of theta. And if you do that, the book shows you, but not in a lot of detail, quite honestly, but you know, y'all are really good with math at this point, so you can go fill in detail. You're going to get new coefficients, a prime, b prime, c prime, d prime. These coefficients are still complex, but if you rewrite your wave functions instead of sines and cosines, you're going to introduce some sort of more explicit looking complexness into the wave functions, into the functional forms of them. It'll just look more complex. The truth is it was complex from the get-go. Yeah, so you end up with these new coefficients. These new coefficients absolutely are related to the old coefficients, and quite simply, quite honestly. The problem is, the hard part is to figure out how these coefficients are related to, it's about the coefficients themselves. Okay, so what's interesting is, so that's one piece of interesting thing. Another piece of interesting thing is to take, time independent. So time independent, that's what this stuff is. It came from the time independent Schrödinger equation, and make it time dependent. So the way you make it time dependent is you simply multiply by e to the minus I omega t, where omega is the energy of our little particle divided by h bar. So this, so that's not an x. This is, it's what you have to do is multiply your time independent answer by this time dependent factor. That turns out to be the answer for how to make this thing time dependent. The truth is the story of time dependence is much more interesting than what I'm saying. And in the future of your physics learning, you will likely interact or have to resolve this for yourself later. But for our purposes, for our class, this is enough to get a time dependence. So when you take this time dependence and made it up with rewriting your wave function in this more explicitly complex looking way, something super cool happens, because what you end up with is right and left moving waves. And these waves are waves of probability density. So these right and left moving waves are going to be what comprise what's referred to as the time dependent probability density function. And like up above, we had two regions. This is also regional. So there is a time dependent piece in region 1, and there is a time dependent piece in region 2. And what's more is each of these things has a real and an imaginary, or these are complex. So let me put it this way. There's a real part of psi 1, the time dependent thing, and there's an imaginary part of psi 1, and then there's a real and imaginary part of psi 2. So